Okay, one more video about confidence intervals. This time we're going to focus on proportions. So this time our data will be binomial with only two possible outcomes. This also means that we will be using the normal approximation mentioned in the central limit theorem video, but we don't have to worry about the continuity correction, so don't worry about that. When you come across data like this in the real world, probably the first thing that you'll notice is that the data are categories, not numbers. And I want to stress the difference between this video and the two previous ones. The previous two videos dealt with numerical or quantitative data. If you survey people and ask about their age, height, and GPA, then they would respond with numbers. Since the data were numbers, we could add them, average them, and do many other possible calculations. The two previous videos focused on the means, but that isn't the only thing that you could do. In this video, the data will be categorical or qualitative. If you survey people about eye color, or religion, or favorite soda, or internet service provider, then they would respond with categories like green, or Buddhist, or Coke, or true online. Most calculations are pointless with categorical data. You can't average them or find their standard deviation, for example. The only thing that we can do is to count them and find proportions or percentages. For now, we'll focus only on binomial data, so there will only be two possible outcomes, called success and failure. The parameter for this kind of data is the population proportion of successes, called P. You could also think of this as the probability of success. For example, if P is the proportion of men in the entire population, then the probability of randomly picking a man would also be equal to P. Like all parameters, we won't know what P is equal to, so we're going to estimate P by collecting the sample of observations and calculating the sample proportion, also called p-hat. P-hat is defined as the number of successes in the sample divided by n. And from the normal approximation to the binomial distribution, we can deduce that the distribution of p-hat is normal with a mean equal to p and a standard deviation equal to the square root of p times 1 minus p over n. So we have this z formula that we'll use in this video and in future videos about proportions. Let's put this to use. We have a sample size of 400. Out of them, 124 said yes, and we're going to make the 90% confidence interval for P. We begin as usual by finding the middle 90% of the z distribution. We know that this lies between plus and minus 1.645. Now we replace z with our new formula for z and plug in p-hat, which is equal to 124 over 400, or 0.31. And now we would normally solve for p, but p shows up 3 times in this expression. And it's going to be really hard to solve for it. So we're going to do a little cheat. We're going to replace each p in the denominator with p-hat. This substitution, of course, changes the answer, but so slightly that the difference is meaningless. And we get a much simpler equation to solve, and that behaves just like the previous videos. So plugging in p-hat and n, we get this. And solving for p is fairly simple. So P is between 0.27 and 0.35 with 90% confidence. So we're 90% sure that the percentage of people who travel abroad is between 27% and 35%. And the form of the confidence interval is familiar to what we've already seen. The center of the interval is equal to p hat, and the interval extends plus or minus z times a standard deviation. It looks like this. Next, we're going to try a sample size question. We want n such that p hat is within 0.01 of p with 90% confidence. And we assume that p is no bigger than 35%. Okay, we've already seen questions like this in the past. We know that this question is all about half-width. Beginning with the confidence level, we know that the middle 90% of the z distribution is between plus and minus 1.645. Next, we replace z with the formula for z. But this question takes place before data is even collected, so we don't yet have a p hat or n to plug in. This is why we have to make the assumption given in the question that p is equal to 0.35. You have to plug in something for each p in the denominator in order to make progress in this question. So there must be some given assumption about p in the question. However, if the question makes no assumption about p, then you should set p equal to 0.5, and I'll tell you why during class. But this question tells us to assume that p is 0.35, so we plug that in. Now we should multiply through the equation by the square root in the denominator. And the question says that we want p hat to be within 0.01 of p. So that means that the half-width must be set equal to 0.01. We can now use this to solve for n. We eventually get root n is equal to 78, and so n is equal to 6,157. Remember that in a question where the sample statistic needs to be within a certain distance of the parameter, then the half-width of the interval would be set to that distance. In this question, it was set equal to 0.01. All right, last question. Let's say we're given a confidence interval and we want to figure out what confidence level is being used. We've done this before, and the first thing that we need to do is find p hat by finding the center of the interval. So p hat is equal to 0.098, and the interval can now be written as 0.098 plus or minus 0.0204. And we can now use the half-width of the interval to solve for z. Plug in p hat and n and solve for z. After solving, we get z equal to 2.17, which is a little unusual. This is not a common confidence level, but let's look it up in the z table and see what it says. The z table says that the area in the tail beyond 2.17 is 1.5%. So in both tails, that means we have 3% area, which means we have the middle 97% of the distribution. Therefore, this is a 97% confidence interval. Okay, you have 3 questions to do on your own now. Good luck with that, and I'll see you in class.